till now we have seen that a grammar is of two types, which is ambiguous grammar and second one is unambiguous grammar. So if we have more than one past tense, then the grammar is ambiguous. So this ambiguity will create problems for the passer, and if the grammar is unambiguous, then it is okay for the passer. So this ambiguity or the ambiguous grammar, we have seen that can be resolved by following two rules. One of them is associativity and the second one is precedence. So all we have done this in our previous lecture. So today we will move to recursion. Okay, so today we will see that left recursion grammar, how to identify that the grammar having left recursion and how to resolve that left recursion. Okay, so recursion is of two types. One is left recursion and second is right recursion. So if the grammar having left recursion, then mostly top down parser fails in this case of left recursion, but in case of right recursion it is okay for the parser. So if a grammar having left recursion, then we have to identify, first of all we have to identify that the given grammar having left recursion, and if there is left recursion, then we have to resolve that left recursion. Okay, so let us understand all this with the help of example. Okay, for example, I am having a grammar in which A derives A alpha beta, and in the second case A derives alpha A beta. Okay, so in this case the leftmost element, left hand side, which is this one, okay, is same as leftmost element of production. Okay, this is that one. If this is the case, then the given grammar having left recursion. Okay, if I am repeating it, if the left hand side is equal to leftmost element of the production, this and this, then we can say that the given grammar having left recursion. And in this case, if I am having left hand side, which is this one, is equal to rightmost element of production, which is this one. If this is the case, then we can say that the given grammar having, or given grammar is with right recursion. Okay, so if this is the case, right recursion, then it is okay, not an issue. If this is the case, then top down parser will fail on that. So if I am facing this left recursion in grammar, then we have to resolve it. So now one thing is that you can also identify that left recursion with the help of parse tree. Okay, let us see that parse tree. Given grammar, the parse tree for the given grammar generally having in which A is the start symbol. So we can say that A derives A alpha. Okay, so further A derives A alpha. A derives A alpha. A derives A alpha. Okay, so one thing that we note that the expansion of this parse tree is along left side. Okay, so we can say that the grammar having left recursion, but in this case the expansion of the parse tree is along right direction. Okay, this one. So this is the case of right recursion. Okay, so once we have identified that the grammar or the given grammar having left recursion, now we will say that how to resolve that left recursion. So by taking the example of the grammar which was A derives A alpha and beta, and in which in this case A derives alpha A beta, it is okay. Okay, but here is issue which will not okay. Now we will resolve that. So the language generated by this is beta and alpha star. Okay, so the language generated by this grammar is this one. So we will change this grammar to a grammar which is not left recursive without changing that grammars. So now let us see how we can do this. So this can be written as beta A dash. Okay, but this is not a grammar, okay, so we can change this to A derives beta and A dash and A dash, which is equivalent to alpha A dash and summation for carrying its productions. Okay, so for the grammar G1 we have resolved this grammar to this one. Okay, so let us write it here. We have grammar in which derives A alpha beta, and this grammar is equivalent to A derives beta A dash, and A dash derives alpha A dash and mission. Okay. So this grammar, we have changed this grammar to this one, and in this case the given grammar is with left recursion, and this one is without left recursion. Because this one is different. Okay, so we can say that the grammar is without left recursion. We have resolved this grammar to this one, and all the language of the grammar is same, but this one grammar is without left recursion. Okay, so let us see this left recursion with the help of one example. So the examples, I'm having a grammar in which E derives E plus T and T. So here, first of all, we have to identify that the grammar having left recursion or not. So the given grammar in which the left hand side, which is this one, which is equal to the leftmost element of production, which is this one. So now, first of all, we have identified that the given grammar is in left recursion. Now, how to resolve that left recursion? So take it as A, okay, this one, and this one is also A, and take this whole as alpha, and this one we take it as beta. Okay, so this grammar we have alpha here. Okay, sorry, here is, this one is A, this one is A, alpha is at this one, and this one is the beta. So we will change this grammar equivalent to this one. So how? Let us see. Here A is, we have, or we can say that A we have E, okay, alpha we have plus T, beta that we have is T. Now change this one to, in which A, which is E, derives beta, which we have is T. Okay, so T, beta. Now A dash is, A is E, so A dash will be E dash. Okay, so now come to here, in which A dash is E dash, alpha we have is plus T, we can write it as plus t. Then we have a dash, which is e dash, and now we have add this summation too. Okay. So grammar, this one grammar is with left recursion, and this one is equivalent, and the grammar without left recursion. Okay, so let us take one more example. Take one example in which we have P derives P O P 1 P and 0 1. So the grammar having left recursion because this and this elements are same. So we can say that the grammar having left recursion. Now resolve that left recursive grammar to grammar which is having no left recursion. So here we will take it as A. Okay, this one is also A, and this whole is taken as alpha, and this one we take it as beta. Okay, so now we change this grammar to equivalent to this grammar. Let us write here A is P, alpha is 0P, 1P, and beta is, okay. So now we write it as A in this one, but A is P derives beta, and the beta is 0 1, but write it as 0 1 A dash, and if A is P, then A dash will be P dash. Okay, and A dash or P dash we can say that alpha, which is 0P 1P, 0P 1P, and A dash, which is P dash, and next is summation. Okay, so we change this left recursive grammar to the equivalent grammar, this one which having no left recursion. Okay, so let's take one more example on this left recursion. Grammar in which T derives into X, which P derives P comma T slash T. Okay, the given grammar is this one. So we have seen that in this case, in this line, we have no left recursion. Okay, but in this case, this one and this one is same, so it having left recursion. Okay, so now we will solve this left recursion. So let us do this. P and comma. So now this P we will take it as A, this we will take it as A, this whole we will take it as alpha, and this is as beta. Okay, so we write it as A is P, alpha is, and beta we have P. Okay, so now convert this grammar or resolve the grammar and left recursion. This grammar become equivalent to here A is P, so we write it as P, beta is T, beta that is T, and now A dash means P dash, and now P dash will be equivalent to alpha, which is this and this, and here A dash means P dash and summation. Okay, so the given this one grammar is having left recursion, and this one no left recursion. Okay, so let us take one more example.